So the space spanned by a set S is denoted by span S. It should be noticed that the space spanned by S is the smallest subspace of V which contains S. There can be larger subspaces of V which contain S, but the state spanned by S, the elements in S, is the smallest subspace of V which contains S. Also, one obvious fact that the span of S, which is the subspace of all the linear combinations of elements in S, is, of course, it's the same for any reordering of vectors in S. Doesn't matter which way you add up the vectors or reordering of the set of elements in S, the span of S will remain the same. So here is a proposition. Let S be a set of vectors V, and let W be a subspace of V. Now if S is a subset of W, then the span of S is contained in W. So, which is to say that, what does it mean? It means that if the elements of the set S belong in W, then this implies any linear combination of S is in W too. And since W is closed under addition and scalar multiplication, is closed under addition and scalar multiplication, well, this means that the span of S is also a subset of W. Now we come to an important concept of linear independence. First, let's define, so what's a linear relation among vectors? So a linear relation among vectors is any relation of the form equals to 0, where of course each of Ci belongs to the field F. Now the set V1, V2, Vn are linearly independent if there is no linear relation among the vectors in the set except for the trivial relation where all c sub i's are 0. So in other words, let this set be a linearly independent set, then from the equation we can conclude Ci is 0 for every I, or in other words, we can also say that if we've been given then this can occur only if 0. Then this means that the vectors are belong to a linearly independent set. So a few things to be noticed is that consider a linearly independent set. This property holds for ordered pairs. There cannot be any repetitions. For example, I cannot have V1, V1, V2. This is not a linearly independent set simply because I can have V1 minus V1 equals to 0. That's a linear relation and that's non-trivial. Also, so this is one. Second point is no vector of the set that is linearly independent can be 0. Well, because if V1, Vi is 0, that's a linear relation. So that makes it a linearly dependent set. One important and interesting thing is that the linear independence of vectors has an intimate relationship with linear system of equations. For example, if I am being given V1 as V2, consider V3 as. Now I can express it in terms of a matrix A is 1 0 1 1 2 0 2 1 2. And what does a linear relation mean? Well, a linear relation is nothing but some combination of this sort, which in the matrix form would be AX, where X is this vector. So AX equals to 0, consider this equation. So we can seek solution to these equations. AX equals to 0. So remember, this was V1, V2, V3 as column vectors. And this also represents a set of equations. It also represents a linear combination of vectors. So for a linearly, we notice that for a linearly independent set of vectors, the equation AX equals to 0 only has a trivial solution. That is to say, this to be 0, all x1, x2, x3 has to be 0. In other words, this equation has a trivial solution when x1, x2, x3 is equals to 0. Which means x1 equals to x2 equals to x3 equals to 0. I can write A as v1, v2, v3, which means all these guys are 0. And what's the condition for that? We know from the system of equations of this form, well, the determinant of A, if it is not equals to 0, then the vectors are linearly independent, and we have a system of equations which only has a trivial solution. What happens when you add a fourth vector? A prime equals to, let's add another vector, some fourth vector, v4. And now I have 4 of these because I need to have a linear combination of 4 of them. Let me consider this set of equations. So what is this? If I expand it, I'll have 3 equations. If I multiply and express it as equations, I'll have 3 equations and 4 unknowns. What are the 4 unknowns? x1, x2, x3 and x4. So anything of the form of m equations in n unknowns such that m is less than n always has a non-trivial solution. You can check that. So in other words, I don't have 4 vectors which will be linearly so this will have a non-trivial solution. That means there would be a solution other than x1 equals to x2 equals to x3 equals to x4 equals to 0. And deeper reason is that my space V was column vectors from this field, m dimensional column vectors, and as long as m is greater than n, greater than or equal to m, I have a possibility where n is my number of vectors I am considering, whether or not they are linearly set of vectors. So there's always a possibility of linearly independent n number of vectors. But the moment I have m less than n, then I have got m equations in n unknowns, and I have a non-trivial solution to that, and I lose my linear independence. So that's how we connect linear independence to solution for the system of equations. Thank you.